Okay, let me first make the diagram for this problem. And there is a mass A that is coming along this line. And this reflects back in this direction. And the reflection angle is alpha. So this angle is alpha as well as this angle, both are equal to alpha. And they call this point as O. And there is a point O dash here. There is a distance of L below. So this point O dash, that is L below from O. Now let me read the question. A disk of mass m, so this is a disk of mass m, sliding over a smooth horizontal surface with velocity v. The velocity of the disk is v. And now this whole system is kept on a horizontal surface. So you see what is happening on the horizontal surface. So this is the horizontal surface. And there is a ball at this end. So a ball is coming, this is something like carom board. So this ball is coming in this direction and reflects back in this direction. And if I look from the top view, it will look something like this. So this is the top view. Are you getting? So this is the top view. It will look like this. So this ball is coming this way at angular alpha. This reflect back and collide with this ball. So the same thing I can plot here. So this is the ball. This is coming this direction. It's going back with angle alpha. Now question says, a disk mass m sliding over a smooth horizontal surface with velocity v experiences a perfectly elastic collision with a smooth stationary ball at point O. So there is an elastic collision at point O. So collision is elastic. So we will have in this case elastic collision. So you're getting. Now question also says the angle between the motion and direction and normal to the ball is alpha. First part of the question says, what are the points relative to which angular momentum of disk remains constant in the process? So we have to find points about which angular momentum remains constant, about which angular momentum is conserved, about which L is constant. Now let us discuss this part first. So what are the points about which angular momentum is constant? So if you see, can you think for 1 minute? What are the points about which angular momentum is conserved? Now you have to think about the impulsive forces. You see, at the time of collision, when this block on this ball collide with this surface, there is an impulsive force that is acting as a normal reaction. Now this normal reaction, initially this system is coming in this direction and this is going in this direction. At the time of collision, there is a normal reaction that is acting, that has an impulsive action. Now if I consider any point on this line, so on this line if I consider any point, normal reaction will have no moment, no torque about this line. So if I consider any point on line AB, let us call, or AB if I already written, then let us call A dash B dash. If I consider any point on A dash B dash, normal reaction will have no moment, no torque. So if there is no torque, this means angular momentum will remain conserved, because dl by dt is equal to torque external. If torque external is 0, this suggests me dl is equal to 0, dl is equal to 0. So this means L is equal to constant. So this means any point on A dash B dash line will give angular momentum constant. So my point is, so points can be taken on A dash B dash. So any point on line A dash B dash will give me the constant angular momentum. Now let us discuss B part. B part says the magnitude of increment of vector of angular momentum related to point O dash, which is located in a plane of disk at a distance L from the point O. Now this means if I take a point on this, angular momentum is constant. But if the point is not located on this line, so let us say this point O dash. If I consider the point O dash, angular momentum is not constant, it will increase. And the question said to how much it increases. So what is the increment in angular momentum if I consider point O? So what is the angular momentum increases about O dash. So this is my O. This point is O and this point is O dash. That is basically L distance below. Are you getting? Now if you see, let us say, if I consider just before collision, this is here. So what is the direction of velocity will have? This direction and velocity is in this way. V is in this way and the collision is elastic. So I can say it will have two components, in this direction and this direction. The velocity in this direction, so it will have two components, this direction, one component of velocity, and if you have another component of velocity in this direction. So this angle is alpha. So this angle is again alpha. So this will be V cos alpha. This is V. So this will be V cos alpha. I think you are able to see this one. And this is V sin alpha. V sin alpha passes through the point O dash. So it will have no angular momentum. So initial angular momentum I have about point just before collision about point O dash. This will be equals to mvr. So mv cos alpha and the distance is L. So I have to multiply by distance L. So this is the initial angular momentum. Are you getting? So this is the initial angular momentum. Let us calculate the final angular momentum. So if I make a diagram for final angular momentum calculation, what you will have is, now the object is basically, the collision is elastic, so it is moving in this direction with the same velocity v, and this angle is alpha. Again I can take, so this is the point O dash at a distance L below. So I can say velocity have two components, in this direction and in this direction. So this angle is again alpha, so you will have V cos alpha in this direction, and in this direction you will have V sin alpha, that basically passes through the point O dash, so it will not contribute to the momentum, angular momentum. Now LF will be again m V naught cos alpha into mv cos alpha into distance L. Now what is the sign of this angular momentum? So this angular momentum is in this direction, so this will basically, this will, so there is a point, this is the B velocity of V, so this will try to rotate in this way. So I can say this rotation is in this way. Now if you see the previous one, so you see how to find out the direction of angular. So let us consider this point. If this vector, the velocity V cos alpha, will try to make something like this kind of motion, that is a anti-clockwise in this case. The previous one, if you see, and this vector velocity V, and this will try to rotate in this way, that is a clockwise. Are you getting? So this will move rotate in clockwise, and the previous latter one will anti-clockwise. So what is change in angular momentum? Delta L, that is L final minus initial, and final is mv cos alpha into L, and the direction is this. The previous one is mv cos alpha into L, but the direction is this. This is the, okay, so let me see the direction for previous case. So I have written here, so this is in this direction. Are you getting? That is, one is clockwise, another is anti-clockwise. So this is clockwise, this is anti-clockwise. So if I take this as a negative, if I consider initial direction as a negative direction and final direction is a positive. So this will become 2mv cos alpha into L. So this is 2mv cos alpha into L, and direction will be this. Are you getting? So you can say 2mvl cos alpha, and the direction is this. So this is the delta L, change in angular momentum. So this is the angular momentum increment. So how much angular momentum increases? So this increases by 2mvl cos alpha. So you see, in this case, if you see this problem, this is a good problem in the sense that in this case angular momentum about point O is conserved, but angular momentum about point O dash does not conserve. Basically about point O, the normal why this is not conserved? Because normal reaction that is acting on this ball will exert a torque about point O dash. About point O dash, normal reaction has a torque, and that torque will increase the angular momentum. Why it will increase? Because force is acting, torque is acting, so angular momentum will increase on this system. Are you getting?